Hello everyone, welcome to the 17th lecture for our course Irrigation Engineering and Hydraulic Structures. In today's video, we are going to start our new design theory, which is Lacey's theory for canal design. And again, you need to remember that this theory is also for design of alluvial canal, right? Previous theory, Kennedy's theory, was also for the designing of alluvial canals. Similarly, this theory, Lacey's theory, is also for the designing of alluvial canals. Okay. As we have discussed in the Kennedy's theory, that Kennedy gave his theory in 1990. Kennedy's theory was given in 1835, right? 1830 or 35, I'm not sure, let me check it out. Yeah, it was in 1830, right? And what Kennedy said? Kennedy said that according to Kennedy, stable or rhyme conditions of a canal is when there is no silting and no scoring, right? This is what Kennedy said. And we have also discussed few other limitations of Kennedy in our previous lecture. And according to Kennedy, these were the limitations, right? You need to look into these limitations. And he didn't consider the concentration of silt, right? Silt concentration too. So what Lacey did? Let's move into the Lacey's theory. Lacey actually investigated. He didn't perform any new experiment. He actually investigated the Kennedy's theory. He investigated in the Kennedy's theory, okay, and find out various drawbacks and limitations in Kennedy's theory, okay. As we know, according to Kennedy, we know that as we have written here, stable or rhyme conditions of a canal is when there is no silting and no scoring. But Lacey contradicted this statement, and he has given his own statement. According to Lacey, a canal showing no silting and no scoring cannot be always in a rhyme or stable condition. Got it? Kennedy said that if a canal is showing no silting and no scoring, then it is going to be in stable condition every time. Always it is going to be in regime or stable condition. But Lacey contradicted this statement, and he said that a canal showing no silting and no scouring cannot be always in stable or regime condition. Okay, what was the regime condition? We have defined that regime condition, regime or stable condition means equilibrium condition, right? That means silting and scouring both are 0, or you can say that silting is equal to scouring, right? This is known as regime or stable condition. So after giving this statement, what Lacey did, after his investigation, Lacey defined 3 regime conditions. What were they? The first one, he named it initial regime condition in a canal, and second one he named as true regime condition of canal, and third condition he named as final regime condition or stable condition of the canal. Okay, so what are these initial, true and final regime conditions? What was his base of study? As we know that whenever, let's try to draw out a figure. Let's say this is our source, right? Whenever a canal, alluvial canal, starts from a source like river, initially the width of the canal is narrow, right? With the passage of time it starts increasing. Got it? From the source, let's say this is our source. Let's say this is our source. Source can be a river, and this point is, let's say this is our start of canal. Okay, this point is start of canal. So at the start of canal, this is actually narrow. Okay, with the passage of time, the dimensions or cross section of the canal will start increasing, and after that a time will come when the cross section will become constant, or dimensions will remain constant. And at the end, what is going to happen? At the end, this water will fall into a, let's say, ocean, right? Got it? So there are actually 3 phases. Let's divide them. The first phase is from the start, right? Let me use a different color. it is overlapping the writing, so let me use red color. From here to this phase, right? The dimensions of canal are been changing, and it from at the start it was narrow, and with the passage of time, its cross section and dimensions start to change and start to increase. After that, in second phase, the dimensions or cross section of the canal remain constant, and in the third phase, the water will fall into the ocean, right? So on the basis of these three, he has divided the regime condition or stable conditions of a canal into three phases: initial condition, initial regime condition, true regime condition, and final regime condition. So this phase, he called it, the first one, it is initial regime or stable phase of canal or condition, and this he called true regime condition, and this one, the third phase, he called it final regime condition before falling into the ocean. Okay. So in this initial condition, you can see that the dimension is changing, right? Here, cross section changes, and slope, bed slope also changes. Here almost every parameter is constant, so that is why it is known as true regime canal. And actually in alluvial canals, this condition doesn't fit. This condition is only true for artificial canals. Okay, and this is the final regime condition. In this case, there may be settlement of large silts in these areas, right? Silt or large sediments will settle here in this region. Got it? So this is known as our final regime condition. So let's try to write down important points for all these three conditions. The first one is initial regime condition of canal Write down these important points. For initial regime condition, the first important point, it is the condition. We are just making notes as we have discussed in the previous figure. It is the condition, or you can say it as the first stage after canal gets into service, right? And in this stage, canal cross section is formed initially, but canal bed slope keeps on changing. Okay, means that it is formed during initial regime conditions. So due to this change in slope, due to change in bed slope, or we call it longitudinal slope, the canal depth also changes. Okay, obviously if the bed slope or longitudinal slope of the canal will change, ultimately its depth will also change, but the width remains same in this stage. Okay, so how in this condition, how canal is going to achieve stability? Hence in this phase, canal will achieve its stability by changing, or maybe you can say by changing or by varying its depth. Got it? And all other parameters remaining parameters of canal will remain constant. Remaining parameters means discharge of canal, silt grade or silt charge. We have discussed all these terms in the Kennedy's theory, and width. All these will remain constant. Okay, so these were a few important terms related to the initial regime condition. The second condition is true regime condition. In true regime condition, all the parameters will remain constant. If all the parameters are constant, that means that is true regime condition of the canal. Okay, so this is only true in case of artificial canals, okay, where there is no silting and no scoring. This condition is only true in case of artificial canals. Hence, we can say that artificial canal constructed having fixed cross section, bed slope and other parameters then its total incoming silt grade is equal to outgoing silt, okay, silt grade or silt quantity, and this is known to be an ideal condition. This condition is an ideal condition of canal which is not possible practically in case of alluvial canals, okay. Alluvial canals that's it. Let's move to the third condition. Third condition is our final stage or final regime condition, okay. What are the important points we have discussed about the final regime condition? In final regime condition, we can say that it is the final stage of canal, or maybe in some cases river, in which cross section weighted parameter silt charge, depth, this is the depth along bed slope, vary or change as per discharge, okay. It will depend upon the rate of discharge. So what does this mean? It means that discharge and silt grade becomes constant and all other parameters in this condition are adjusted as per discharge. Got it? These were three important conditions which Lacey defined after investigating the Kennedy's theory. Okay. Other than this, there are few more important points we need to note them down. Then after that we will move towards the design steps. So some other important points include they are also dependent on the previous discussion we have done. Initial rhyme condition in rhyme or a stable canal initial rhyme condition is not constant. Write it here. Let me correct this sentence structure. Initial rhyme is not constant in rhyme or stable canal according to the previous discussion, right? Based on the Lacey theory. Even if it shows no silting and scoring, right? From the previous discussion we can conclude that according to Lacey, initial rhyme is not constant in rhyme or stable condition even if it is showing no silting or no scoring, right? But Kennedy said that if there is no silting and no scoring, then canal is going to be in stable or rhyme condition. But the another point we need to note here is that this the previous point was related to the initial rhyme condition, but the rest of two conditions which are true and final conditions are considered as stable or rhyme conditions by Lacey. Okay, so you can say that according to Lacey, he has divided it into three phases, right? Initial, true and final. He said that in initial rhyme condition, even if there is no silting and scoring, we cannot call it rhyme or stable condition, but you can find the rhyme conditions in true and final stages. This is what Lacey said. Okay. Hence, what we can conclude from these points? Hence, according to Lacey, we can say that Lacey's theory is applicable for true and final rhyme conditions and not applicable for initial rhyme condition. Got it? Let's move to the next page. There is one more point we need to note down. So the next point is number of independent equations which form Lacey's enzyme conditions are three. We will discuss them later. And in the final stage or final enzyme condition, the shape of canal will be shallow and wider for coarse silt and will be deep and narrow for fine silt. Got it? So as we said in this figure that in the final stage there will be large sediment which will settle down and they will form. There can be three conditions. Either the canal can be, it can be shallow and wider, right? It can be shallow and wider, or it can be second condition, let me use different color, and it can be narrow but deep, right? So if it is shallow and wider, that means that it is for coarse silt. If there is coarse silt, then your canal at the final stage, final enzyme condition will be shallow and wider. But if the silt is fine silt, then your canal at the final stage will be narrow but deep. Okay, it will be narrow and deep for fine silt. For coarse silt, it is going to be wider and shallow. Okay, so these were some important points related to the Lacey's theory on the basis of his investigation. Let's move forward and try to discuss the design steps. Design steps involved in Lacey's theory for alluvial canals. Okay. Design steps. If you remember the design steps of Kennedy's theory, we have in the first step we have find the critical velocity, right? And at the end we find the actual velocity, and we compared both velocities to decide either we are going to change the depth of the canal or not, right? But in this case we are not going to find two velocities, critical and actual velocity. We are just going to find one velocity that we will represent with V. So in the first step, again we are going to calculate the first step is velocity of flow represented with V. Okay. So in first step, what is the formula? The formula we got for V, velocity of flow, for given by Lacey, is V is equal to Q F square and then divided by 140 and whole raised to the power 1/6. This is the formula to find out the velocity of flow. This is our first step. And how we can find F here? F is equal to 1.76 under root D. Okay. So in these equations, what is V? As we said that V is equal to velocity and Q here is discharge given to us, and F here is, it is known as silt factor. Okay. And what is D? D is particle size, or you can say silt size. Or you can name it average diameter of particle size. And what are going to be the units of these variables? Velocity meter per second, discharge meter cube per second, silt factor, it is unitless, and D, particle size, silt size, it is in millimeters. Okay. So this was our first step. In second step, similar to the previous theory, we need to find mean hydraulic depth. We represent it with R, right? So here, to find out the mean hydraulic radius, we have a formula, which is mean hydraulic radius is equal to A divided by P. Or there is another formula in case we need, because it depends upon the data provided to us. R is going to be equal to 5 divided by 2 multiplied by V square. V square is the velocity which we have found in the first step, divided by F. F is the silt factor, right? So these are two formulas to find out the mean hydraulic depth. What is A here? A is equal to cross sectional area, and what is P? P is equal to weighted parameter. Okay, and the units will be area meter square, weighted parameter will be in meters. This is our second step. And the third step of our design phase is to find out the area of cross section of canal, right, which is A. For that we got the formula which we used in previous theory too. A is equal to area, cross-sectional area is equal to discharge divided by velocity. Okay. In the fourth step, we are going to find wetted parameter. Wetted parameter, which is represented with P. For wetted parameter, we got formula wetted parameter is equal to 4.75 under root Q. Okay, this is the formula. Q is discharge, P is wetted parameter. So you can maybe get some sort of multiple choice question from these formulas. From this formula you can see that wetted parameter is directly proportional to under root Q flow. So if discharge is increasing, that means that your wetted parameter will increase too. Let's move to the next step, which is our fifth. In fifth step, we will find the longitudinal slope or bed slope. We represent it with S. For that, we have a formula to find out the longitudinal or bed slope, which is given as S is equal to longitudinal or bed slope is equal to F is Silt factor raised to the power 5 by 3 and divide it with 3340 and Q raised to the power 1 upon 6. This is the formula to find out the slope. Okay, these were 5 steps. We will follow these steps to design alluvial canal using Lacey's theory. This is our fourth step. This is our third step. This is our second step. Actually, this theory is simple and it's not lengthy comparing with the Kennedy's theory. Okay, these are the steps. And after that, we need to note down a few more important points before going into the numerical problem. There are 2 more formulas we need to remember. We have discussed eddies, right, in the Kennedy theory. Kennedy said that eddies in a canal only generates from the bed of the slope. But Lacey said that eddies can be generated from both the side slopes and bed too. Okay, so according to Lacey, eddies will be generated from both side slopes and bed of the canal. Hence we can say that Lacey's theory is much better than Kennedy's theory for designing any alluvial canal. Okay. And if you are asked to find out, because in this condition, in this theory, Lacey has considered the silt concentration, right? So if someone asks us to find out the normal scoring depth, okay, then we got two formulas, one for normal canal to find out the scoring depth, one is for wide canals. As here Lacey has considered the silt concentration, so we can use formulas or mathematical expressions to find out the depth of scoring in canals, depending either it is a normal canal or a wider canal. Okay, there are two formulas to find the depth of scoring. So what are those formulas? Depth of scoring for normal canal, and the other formula is for depth of scoring for wider canals. Okay, we got two formulas and we represent it with depth of scoring is represented by R. Then in this case, in normal canal, the depth of scoring can be found by using this formula. R is equal to 1.35 into Q square divided by F, Q square divided by F raised to the power 1 by 3. Okay, and in case of wider canal, we can find the depth of scoring by using formula 0.473 into capital Q divided by F raised to the power 1 by 3. Okay, this capital Q is discharge, but what is this small q? This q is per unit width discharge. This is known as per unit width discharge. Okay, so this means discharge per unit of width, which is B, right? This is width. So you can find the value of Q by dividing discharge with the width. So what is going to be the unit of Q? As we know that capital Q discharge is meter cube per second, right? And B is meter. Okay. If this meter cancels with this meter, then the remaining unit is meter square per second. So the unit of this will be, it is going to be meter cube per second divided by m multiplied by 1 upon m. Yeah, this will cancel with this and its square will remain. So the unit of Q is going to be meter square per second. Got it? So these were some formulas and design steps of Lacey's theory. We will wind up this lecture here, and in the next lecture we will consider a numerical problem, and we will follow all these steps to design an alluvial canal using Lacey's theory. So for now, that's it. See you guys in next video. Till then, goodbye. Take good care.